Hello, everyone, and welcome back. Today, we're going to be talking about electronegativity. And so, at the very least, you're going to have a little bit of a Gen Chem throwback, but it's going to be in relation to what we've been talking about so far in organic chemistry. So, with electronegativity, we said at the beginning of this course that covalent bonds essentially just share electrons equally, right? And as a matter of fact, that is not entirely true. Right? Because if we're looking at something like an oxygen hydrogen bond, we were originally saying that this bond right here is equal electron sharing between the two atoms, but that is just a flat out lie. And the reason is because of electronegativity. Right, and this is a throwback to old Gen Chem, so hopefully this won't be too new of a concept. But you may remember from Gen Chem, some atoms want electrons more than others. And so electronegativity is essentially a value stating how much an atom tends to attract electrons in a bond. All right. And so the way that we can really think about electrons and bonds and electronegativity is you can imagine if the bond is like a rope, right? So we have this oxygen and it has a rope between it and a hydrogen, and there are perhaps two electrons on this rope. All right, so those right there are our electrons, and then the orange guy, this is our rope. It's essentially a tug of war between the oxygen and the hydrogen, right? Because the oxygen's pulling electrons towards it, the hydrogen wants to pull electrons towards it. Electronegativity is pretty much asking the question of who wants the electrons more, right? And so what this boils down to is there's this table here that is about electronegativity, right? It has all of the elements on here, at least the ones that we have data for. And as you start to trend towards fluorine, right? Fluorine's all the way up here in the top right corner. This is our highest electronegativity, which you'll notice I will abbreviate to E neg from now on, just to make it quick and easier to write. And on the other side of the periodic table, as we get towards things like francium, so a lot of these metals, this is our lowest electronegativity. And so what that means is the higher your electronegativity, the more you want those electrons, so the harder you're going to pull. So if we once again take a look at this oxygen and the hydrogen with a rope, right, the actual situation of this rope is that those electrons that were sitting on there, rather than being right there in the middle, as a matter of fact, the oxygen is much stronger at pulling those electrons towards it. Right? And so this is signified by the fact that if we look at this electronegativity table and we find where oxygen is, right? It's right up here. I'm circling it in pink. It has a value of 3.44, whereas hydrogen is sitting over here at this 2.20. Higher number essentially wins. And so what that's showing is that the oxygen is putting in all this work, right? It's got a lot of force pulling those electrons towards it. Whereas our hydrogen is not putting in as much work to get those electrons. It doesn't want them as badly. And what this does is since the oxygen is holding the electrons closer, right? That's essentially what we're showing. Oxygen holds those closer. So it technically has more electrons. And this creates what we call both in Gen Chem and in organic a dipole moment. And what a dipole is it's a separation of charge which is generated from an unequal sharing. of electrons, right? And so what that means is whenever we're looking back at this picture of the oxygen-hydrogen bond, what's actually happening is we're going to be drawing a dipole arrow on this bond. And the dipole arrow has two parts to it, right? On the far right side, this little cross here, it kind of looks like a plus symbol, right? Kinda. We'll put that in quotes. And it's showing where the charge lacks, or where electrons are lacking, right? We're essentially saying that one atom is pulling the electrons away, and where that positive charge is where the electrons are missing. And the arrow here is showing where the electrons are pulled to. All right. And so these dipoles essentially also give rise to partial charges. Because if we take a look at what's actually happening here, we're essentially saying that oxygen, since we are pulling a dipole towards it, has more electrons than the hydrogens. So in reality, it's creating this charge distribution, and this is the actual definition of the dipole that we're going for. Right? Hydrogen is lacking electrons. It has a partial positive. Oxygen has an excess of electrons, and that's why it has a partial negative charge. And the thing to remember here is that charges, oftentimes, whenever we're looking at organic chemistry, they determine our reactivity as well as molecular interactions. All right. So these charges are really important. And throughout most of the course, we're actually going to be looking at situations where this difference in charges, the positives and negatives, actually changes how our molecules react. But more importantly, one of the things that we're going to kind of turn over and look at now is actually a concept that's important in lab, right? Because at the moment we've been talking a lot about lecture stuff, and a lot of the lecture will start to blend in with the lab. But one thing that you need to make sure that you know is actually there are some other things in lecture that will blend into the lab. And this one, although we're not going to focus too hard on it for lecture, you're going to focus on it a bit in lab. And that is another friend from Gen Chem, intermolecular forces. Or, as you called them back then, they are IMFs. And what these IMFs are is they are forces that occur between molecules, right? And so these forces are going to sort of keep molecules together or kind of not keep them together. So forces that occur, oops, sorry about that, between molecules. And we have four different types. Now, you're probably used to three of these, but the fourth one is also a little important for some things later on. So you have ion dipole. This is the one you're probably not as familiar with. You have hydrogen bonding. You have dipole-dipole. And then you have dispersion, which is also called London dispersion quite often, or as many people now call it for London dispersion forces, LDF. And so these are ranked from what is essentially the strongest being ion dipole interactions and the weakest being LDFs. Okay? So we're going to go through each of these and we're going to talk about why they're important because there will come a lab later on where intermolecular forces are the entire purpose of the lab. So let's start with the weakest and work our way up. We will start with dispersion, also known as LDFs. So London dispersion for forces are something that everything displays. All right, so it happens due to proximity and induced dipole. And essentially what that means is if you have two molecules of, say, butane, right? So here's the structure of butane. Them being close to one another essentially creates a very weak attraction. And oftentimes, this isn't important enough to do much for us. All right. It is just entirely due to this proximity and being able to push around dipoles. Which brings us to our second one, a more important one that we care about, and that is dipole-dipole interactions. So dipole-dipole is where two molecules with dipoles interact via partial charges. And so the entire idea of this set of intermolecular forces is that, of course, if you're looking at a positive and a negative, these are going to be attracted to one another. And the same is true if that is a partial negative and a partial positive, right? They will still be attracted. And so if we take, for example, acetone, which is something I'm sure you've all had a little bit of experience with thus far in lab, right? Acetone has a dipole because if we're looking at the structure of acetone, the carbon-oxygen bond is polarized. So polarized just means they have two different electronegativities. And so the electronegativity of a carbon is 2.55 and then oxygen is 3.44. So it's a very polarized bond where you essentially have a dipole pointing towards the oxygen, right? So the oxygen has a partial negative, the carbon has a partial positive, because remember the bigger number is going to take the electrons, oxygen has a bigger number. Then the same thing can happen with another acetone molecule. And so what happens when those two get close, right? So if we push them close together, essentially they'll orient themselves, and I'll draw the bonds a little longer so it's a little easier to show. They orient themselves kind of like this, where the oxygen with the partial minus is close to the carbon with the partial plus, right? Same thing with the other oxygen and carbon. And so these, being so close to one another, essentially will want to come together, right? They are attracted to one another. And so that'll make those molecules interact with each other a little more, which is going to change some physical properties. Right, that's the important part about a lot of these IMFs is it changes physical properties. So something like acetone has a higher boiling point because this interaction keeps them from boiling away from one another. All right. Next one up is hydrogen bonding. And hydrogen bonding is a little more complicated because essentially what it is any OH, NH, or HF, right, interacting with a basic atom such as oxygen, nitrogen, or fluorine. And a lot of this has to do with electronegativity, right? Because again, notice how this is already set up. It's any of these OHs, NHs, FHs, and it's interacting with those same atoms. So if we take a look at something like ethanol, right, here's ethanol, and then we can take a look at something like water. I'll actually draw this bond for everyone. What'll happen is essentially these bonds are very polarized, right? So it's already like having a dipole interaction, where the oxygen is still taking a lot of that partial negative and giving the hydrogens partial positives. But then what they'll do is they'll orient themselves, right? So once again, just like we had seen beforehand with the others, these will also put themselves very close to where the oxygens can interact with the hydrogens. And normally we show this using some dashed or dotted lines. And this is showing a hydrogen bonding interaction. And the thing is, this is essentially the same as a dipole-dipole, but it's with these specific atoms because it's stronger dipole-dipole interactions, right? So this is very strong primarily because of the stronger dipole that's being exhibited. And the way you can think of this is when we were looking at that carbon-oxygen bond, it was polarized to a certain degree, but hydrogen is even less electronegative than carbon. And so the oxygen-hydrogen bond is even more polarized, right? And that's why it's kind of like almost an ionic interaction where the hydrogen is very much so partially positively charged, like very, very, and then the oxygen is very partially negatively charged. So that's how you can think of hydrogen bonding. The very last one that you will not see too much about, but in the future may be useful just to know about, is ion dipoles. And so the way ion dipole interactions work is essentially it is one ion plus one dipole equals strong interaction. All right, and to show how this kind of works, let's say we had a sodium cation, right? So a positively charged sodium, and then we had something like water. What we're going to see is that the water is pulling a strong dipole, right, which is giving the oxygen a partial minus, the hydrogen a partial plus, and that partially negatively charged oxygen is kind of having an ionic bonding effect with the sodium, right? Because these two positive and negative charges are attracted to one another. And the thing is, since it's a full positive charge, it is a strong attraction. All right. So, that being said, you'll get to a point in lab. It is going to be a column chromatography lab, and you will want to kind of look at these interactions and determine how the column, which has a phase that is very prone to hydrogen bonding, how that is going to interact with the molecules that you're looking at. All right. Other than that, in lecture, we're not necessarily going to look at these all that often. I may ask a couple questions about it though. Okay. So let's move on to the next important thing to do with electronegativity, which is resonance actually depends on electronegativity. And that sounds really weird because every time we bring up resonance, there is something else that matters with it, right? At first, it was just resonance. Then it was hybridization is dependent on resonance. And now it's resonance is dependent on electronegativity, right? Because what we were originally saying is that resonance is equal sharing of electrons. However, we have to state here that electronegativity forces resonance to not be equal sharing. So let's take a look at what that means. Well, if we take a look at a structure, one that we've seen a couple times before, that looks like this, and we want to draw a resonance form of it, right? We can draw it to where the nitrogen forms the pi bond, we kick the electrons up to the oxygen, and now we have the double bonded nitrogen that's neutral, and we have the oxygen with the negative charge. These two resonance structures exist, but we have to ask ourselves, which is more realistic, right? A molecule can't be everything at the same time, right? Well, it can be. Resonance is essentially a way that we go through and say that a molecule can be everything at the same time. But one of these is the most likely way the molecule is existing at a single time in terms of how we can draw it. All right, so the question becomes which of these depictions is more realistic? And the answer has to do with which atom has the electrons, right? Because if we take a look at electronegativity, right, let's say that we were comparing oxygen versus nitrogen. The electronegativity value for oxygen is about 3.44, but the value for nitrogen is about 3.04. All right. Oxygen has a higher electronegativity than nitrogen. So what that means is oxygen, I'll write this in a different color. Oxygen wants the electrons more than nitrogen. All right. So if oxygen wants the electrons more than nitrogen, that's telling us that the oxygen wants the negative charge much more than the nitrogen wants the negative charge. So what that's telling us is if we go back up to this little drawing we saw, the one with the negative charge right here on the oxygen, this is the accurate depiction of the molecule. All right. And now what you may be asking yourself is why does this actually matter? And the reason has everything to do with what's going to be happening as we go through organic chemistry, right? What we're going to be seeing is as we go through these reactions, most of them are going to react via the most realistic depiction of the molecule. And so if we were taking a look at this structure here, and we were trying to determine which atom would give away electrons faster, it's probably going to be the oxygen, right? Because it has that negative charge and it has more of those electrons to give away. Okay? And so, with that being said, we kind of have to know what molecules are going to look like. And how we do that is we determine what is called the major resonance contributor, or as we will abbreviate it, the MRC. And so essentially what the major resonance contributor is, we've already defined it. It's the resonance structure that most accurately depicts the realistic dis depiction of the molecule. Okay. So how do we figure out what the major resonance contributor is? Well, we already did it for the one up here, right? We decided that that is the major resonance contributor. But there are other criteria to how we can figure this out in different situations. All right. So there are three criteria for our MRC. So we're going to list them in order of importance. The first one is octets, right? And so what octets essentially means is are all of the octets filled, right? So ask yourself the question, are they filled? All right, we're going to go through examples of each of these and how we're going to decide that. But for now, that's the question you want to ask. The second thing that you have to worry about is electronegativity. And so with that question, you're going to ask yourself, who wants the charge? All right. And then the third one is charge separation. And we'll define this one whenever we get down to it because it's hard to ask the question without showing you an example. So we're going to go through and we're going to give examples for each of these and how the criteria is actually determined as we do resonance structures. All right. So the first one we're going to look at is our first example here, all about octets. So let's say we had a resonance structure, a structure that looks like this, and we are asked to go ahead and draw resonance forms for it. All right. The same as we've always been doing with resonance forms. We look and we see there's a positive charge. All right. That positive charge means that we want to fill it. And how we're going to fill that is going to be through moving this pi bond here. So we can move the pi bond to make a new pi bond between those two carbons. And that resonance form is going to get us to right here, where now we have a positive charge on that carbon on the right side. And we're not done yet because remember, with these positive charges, if we have a lone pair adjacent to where that positive charge is, it can help fill that orbital and make sure that the electrons are where they need to be. So we can draw the lone pair becoming a pi bond right there. And then what we end up with is a resonance form that looks like this. And so now we can ask ourselves, which is the MRC? Which is the major resonance contributor? All right, we will start with our first question, which is octets. Right? We have to ask, are they filled? And we got to go through each of these structures and see if on any of them the octets are filled or if there's any missing octets. In the first structure, that carbon has a positive charge. We know that if a carbon has a positive charge, that means it's missing a bond, right? There is a hydrogen there that we don't show, but there's one bond missing. That's a formal positive charge on the carbon, which means that this one is missing an octet. All right. Same thing with the second structure. We have a positive charge on a carbon. This one right here is missing its octet. But then if we take a look at the last structure, we see here that, oh, the oxygen has a positive charge, but let's remember that the oxygen beforehand did have two lone pairs. There's one lone pair left on it. It has a positive charge, and it has three different bonds to it, one to the hydrogen, two to the other carbon. So this one right here, this has an octet. And since that oxygen has an octet, all of the other carbons there also have their octets filled. And so what that means is when we're thinking about our major resonance contributor, the fact that this has all octets filled means that it is the major resonance contributor for this resonance form. So that is what this molecule most looks like. Okay? Hopefully that makes sense. You're just checking to see if there is anything that has full octets or empty octets. And if there's one thing that has all octets filled, but other things that don't, it's the thing that has the full octets that ends up being your major resonance contributor. Okay, let's move down to our second example. So for this one, let's take another molecule that we can draw resonance with as an example. Yeah. So we'll do this one here. And we'll just draw out all the resonance forms for it. So the sulfur has a negative charge. It wants to give away some electrons. We see that it's adjacent to a carbon with a pi bond. So we can form a pi bond from that lone pair there. And then we can take that pi bond and give the electrons to that carbon. That gives us a resonance form where we have that double bond to the sulfur. Nitrogen's still triple bonded, but that carbon now has a lone pair on it and a negative charge. From there, though, it is adjacent to where that triple bond is. So we can draw the arrows to move electrons up to the nitrogen there. And that gives us one more resonance form, where now the nitrogen bears the negative charge. Okay, so this is all the resonance forms that we have here. So now we have to ask ourselves for our major resonance contributor, right? We still have to pay attention to the things in order. So the first one we have to pay attention to is octets. So looking at all these, we have to ask ourselves, are the octets full on every structure? Or are they empty on every structure? The same question applies to both. So here we see in the first structure, no, all octets are filled. Second structure, all octets are filled. Third structure, all octets are filled. All right, so we can say for octets, we're good to go. There's nothing to worry about. So now we move down to our second criteria, electronegativity. So what this is saying is which atom wants the electrons more? That's going to boil down to what is the electronegativity of the atoms. So looking at where the charge ends up on all these, first we have the sulfur, right? When the sulfur has a negative charge, it then moves it to the carbon, and then it moves it to the nitrogen. So we have to ask ourselves, what is the order in which those are electronegative? Now, I would bring up the chart again, but it's all the way up at the top. I will tell you, though, that nitrogen is more electronegative than sulfur, and sulfur is more electronegative than carbon. So what we're saying is that nitrogen is the most electronegative, carbon is the least, but that tells us that the nitrogen wants the electrons the most. And so because of that, we can circle this and we can say that this is our major resonance contributor because of electronegativity. All right. So for electronegativity, you're just comparing the electronegativities of the atoms. If it's a negative charge, it is the atom that has the highest electronegativity, that wants the electrons the most. Okay. Let's take a look at example 3. So for this one, we can draw out a structure that looks like this. So for this one, remember that neutral compounds can still have resonance, right? We can take a lone pair from an atom, make it into a pi bond, then break a pi bond, push it up to a different atom, just like this. And this would give us a resonance form that looks like this. Hopefully by now you're comfortable drawing some of these resonance forms in the way that I just drew that one. Because remember, this is kind of one of those things that you need to know for hybridization. Now, that being said, we don't have any other resonance here. So we need to ask ourselves, what is the major resonance contributor? So the first thing we're looking at is octets. So even though in the second structure there's a positive charge, the nitrogen still has 4 bonds. That's a fulfilled octet. Everything has fulfilled octets. We're good. The second one is electronegativity. So for electronegativity, it's kind of hard, right? Because there's 2 charges in one, there's no charges in the other. It's kind of one of those things where you put a question mark on it and you're not really sure what the answer to it is. But that's where our third criteria comes in, which is charge separation. Essentially, what this is saying is less charges is better, right? That should be pretty intuitive, right? Because whenever we're thinking about charges, charges indicate that something is unstable. So if we look at something and it has multiple charges, we know it's less stable than something that has a single charge or no charge at all. And so the second structure, having 2 charges, means that it's inherently worse. And that tells us that this first one here is our major resonance contributor due to charge separation. Okay? So this is what each of those criteria is kind of looking for. For octets, you're looking for making sure that everything has fulfilled octets. For electronegativity, you're looking at which atom wants the electrons more. And charge separation is the very intuitive, less charges are better. But remember that these are all in order of the most important to least important thing. All right. So if you can fulfill all octets, that is more important than anything else for the MRC. If you then have electronegativity, where the electrons want to be, that's more important than charge separation. But then charge separation is the last thing that you need to think about. All right. So let's take a look at an example of one of these where I don't say what the major resonance contributor is going to be. And I'll let you all take a second to figure it out right after I draw out the question. So for this one, let's say that we were looking at a situation such as this one. All right, take a second to see if you can draw out all of the resonance forms and then determine which is the major resonance contributor and why. Okay, if you've unpaused the video, we're going to go through and we're going to talk about this entire question. So first things first, the oxygen has the negative charge. We can move some electrons around so we can make a pi bond between the oxygen and that carbon, break the pi bond right there, and give the electrons to the carbon itself. So there we go. Now we have a negative charge on that carbon. From here, we can then take that lone pair, make it into a pi bond, break that pi bond, and give those electrons to the nitrogen. And we end up with a negative charge on that nitrogen, and that's all the resonance that we can do. So now we have to ask ourselves, all right, let's go through our major resonance contributor, uh, I guess, criteria, and we'll start out with octets. So, are all octets filled? Looking through, we see oxygen with A, carbon A, yeah. All right, everything's perfect, right? All octets are filled in that structure, because remember, in bond line, there are some things that we don't show, but it is great. All octets are filled. Second thing we have to worry about, electronegativity. For this one, there is a single charge, and it moves around. It ends up on an oxygen, a carbon, and a nitrogen. And if we take a look at our electronegativity table, oxygen is more electronegative than nitrogen, which is also more electronegative than carbon. And so what that means is, oh, hey, well, I guess oxygen, being the most electronegative, is also going to be the one that gives us the major resonance contributor, which is this first one right here, where that negative charge is sitting on the oxygen, right? This is our major resonance contributor due to electronegativity. Okay, great. Let's move on to another example. Then after this, we'll do one more and then we'll move on. So, this next example, we're going to do one that looks a little bit like this. All right, let's draw out some resonance forms for this and see what the major resonance contributor is. So, first things first, looking at this, we have resonance that can go in both directions, right? Let's start out by going towards the right. So we can form a pi bond here, break that pi bond, give the electrons to the oxygen. So there we go. That is fantastic. But like I said, we can do resonance in the other direction as well. So if we redraw this first structure, we can also do it to where it goes to the left. We form that pi bond and we break a pi bond. And that gives us these two structures right here. So now we got to go through our MRC conditions versus octets. Looking at this, all octets are filled all the time. So that's great. We're very happy about that. The second thing, though, is electronegativity. In two of the cases, the negative charge ends up on the oxygen. In one of the cases, it ends up on a carbon, right, the starting. And what we already know is that oxygen is much more electronegative than carbon. So that must mean one of the structures with the negative charge on the oxygen is the major resonance contributor. But here's the thing, we have two different structures that both have that negative charge there. So now we need to ask ourselves for our third criteria, is there any issue with charge separation? The answer is no. Both structures, or well, all structures in this case, only have a single negative charge. So what this means is if you have two structures that end up giving you the exact same criteria for the major resonance contributor, it turns out that both can be a major resonance contributor, and we call those equal major resonance contributors, right? And essentially what this means is you can have more than one major resonance contributor. All right. So looking at that idea, we can move on to our last example, example 6 here. And we can think about, okay, well, if we're going to have something sort of like this, what is it going to look like if we do a little bit of resonance here? So, first things first, we can move some electrons from the pi bond here. Remember, we can't remove them from the double bonded oxygen because if we did so, we would end up making something that is missing an octet on oxygen, which we are not allowed to do. Okay, so we end up with this structure here. And so from here, we have that positive charge that's adjacent to more pi bonds, right? We can then move some electrons. We can move one of those pi bonds to form between these two carbons. And we end up with this structure here. I'm going to use a dot to indicate where that carbon is that is sort of between the two. And then we have a positive charge over here. And that's the end of our resonance forms we can draw. So if we're looking for a major resonance contributor, first thing that we got to pay attention to is octets, right? Looking at this, the first structure has a missing octet. The second structure has a missing octet on that carbon. The third structure has a missing octet on that carbon. What that means is that essentially every single structure that we've drawn has a missing octet. It's the same as having all filled octets, where they're all the exact same. So we can check that off and say that, hey, everything's missing. And we can move on to our second criteria, which is electronegativity, right? For this one, it's just carbon, and carbon is the same across all of them, right? They all have the same electronegativity. So now we got to move on to our third criteria, which is charge separation. And looking at this, we can say, oh, well, they all just have a single positive charge, and there's no way to neutralize it. That's the only charge that there's going to be. So what that means is that everything here we just said is all the same for every criteria of the major resonance contributor, which funny enough means that every single one of these is an equal major resonance contributor. Every one of them. So you can have anywhere from a single major resonance contributor, which is usually the most likely thing that'll occur. You can have two, you can have three, you can have hundreds, as long as they all meet the criteria in the exact same way. All right. But needless to say, when you're looking for major resonance contribution, electronegativity plays a big difference. Okay. And so where that's going to lead us to is we're really going to start talking about how charge interacts with other atoms. All right. And that's going to lead me to the final thing that I want to say for this lecture, and that is all about charge interactions. We've said it many times before, but we're going to rephrase it a little bit here because what we've been talking about a little bit is that negative charges and positive charges attract one another. All right. But what we're going to think about for a lot of organic chemistry is if you have a negative charge and you have a positive charge, the negative charge wants to flow towards the positive charge. And the reason that I'm saying it this way, and the reason I want you to think of it this way, is because essentially we've already talked a little bit about our arrow formalisms in resonance, right? Those curved arrows are showing negatively charged electrons moving towards places that don't have electrons, so more positive charges. And for every reaction we look at from now on, it is always a negative charge thing or something that has a partial negative charge, and it is moving towards something that has a partial positive charge or a full positive charge, right? You want to treat these things sort of in a similar way from now on. They do make a difference in terms of what all they can do, but in the end, the same ideas stay present in both. Negative charges or more electrons will always flow towards less electrons. Now, that being said, the next lecture that we're going to get into is acid-base chemistry, and acid-base chemistry is going to use and abuse this principle over and over again. So we'll see you then, and we will get into the depths of when we start getting to what I would call the first hard part of organic chemistry. See you then.